Hello, I'm Jeff Boyd. In the video you're about to watch, Dr. Lewis Little will talk about how looking at something or measuring it is often thought in quantum physics to somehow define reality, and he'll explain why we think this is wrong. At the end of the video, when he made this video, he realized afterwards that a small variation in the experimental design would allow us to define a new experiment in which the theory of elementary waves and quantum mechanics, or wave-particle duality, predict opposing or different outcomes in the experiment. Now here's Dr. Little talking about the theory of measurement in quantum mechanics.
Greetings, I'm Lewis Little and wish to continue the discussion of the elementary wave theory. One of the, what is to me, most absurd conclusions of quantum mechanics is the idea that looking makes it so. That the state of an object is determined by the act of looking at it, as opposed to a thing being what it is and what you see as a product of what it is. Some physicists have gone so far as to declare that the very existence of something is determined by the act of looking. I expect you're familiar with the somewhat well-known statement by the professor at Cornell, who maintains that it's been definitely established that the moon doesn't exist when no one's looking at it. Now, I'm not sure all physicists would subscribe to that interpretation of what quantum mechanics says, but it brings out rather dramatically what I take to be the absurdity of this point of view. Now, to show how the elementary wave theory resolves this, I'd like to refer to some thought experiments that were presented by Dickey and Whitkey in their famous introductory textbook on quantum mechanics. I've reproduced these drawings, which follow basically the pattern that they used in presenting this issue. In the upper drawing, what we have here is photons coming in from the left, going through a plane polarizer, and vertical come out through one exit and horizontal out another one. The vertical only are fed into a circular polarizer, and it will generate both right-handed and left-handed coming from this originally vertically polarized photon. Only the right-handed ones go into a plane polarizer, and as a result the right hand will generate both vertical and horizontal coming out. So as you feed in more and more photons, you'll see some vertical and some horizontal at the end. And the conclusion from this part of the experiment is that the act of looking here and determining that it's right-handed and not left-handed undoes the act back here of determining that only the vertical ones go through. Because now that you've measured and determined that only the right-handed ones go in here, suddenly you get horizontal ones when there were no horizontal ones at this point back here. So these two measurements of circular or plane polarization are incompatible with one another, and measuring one undoes the other. Now, the elementary wave theory would say that the waves are coming from these detectors. Waves coming from the upper one go through the plane polarizer, and therefore only the vertical comes out. But a vertical will stimulate a right-handed circularly polarized photon. So a circular one will come out, and that circular one will stimulate a vertically polarized photon. So waves will make it to the source. So particles will then follow that wave, and you will see particles at that detector. On the other hand, waves coming from this detector, horizontal waves coming in, so you'll have horizontal coming out, which will stimulate the right circularly polarized, and they come out and will stimulate vertical, and so waves will arrive at the source, and therefore particles will follow that, and you'll see particles at the horizontal side. There's no issue really of this measurement undoing the earlier one. It's just an issue of the fact that both of those waves will make it through to the source and stimulate particles accordingly. Now, the next part of the experiment, or thought experiment, imagine adding what I've called -C here. It's a device that undoes what was done by the first circular polarizer. So whatever is done here by taking the vertical and making it right or left-handed, this will undo that. Now, if you do the experiment as it's pictured, where both the right and left-handed are fed into this device, well, that's what came out here, so you put it in there, and what will come out here will be what went in, and you'll get only vertical. So when only vertical goes into this plane polarizer, only vertical will come out, so you'll see photons here, but you won't see any down here. Now, what you'd expect to see, based on simple common sense, if you were to, say, first block one passageway and see what happens, and then block the other and see what happens, you'd expect that when you had both open, what you'd see would be the sum of what you'd see, because you'd expect the particle would take one path or the other. But that turns out not to be the case. Suppose you block the lower path. Well, then these right-hand circularly polarized photons would come out of here being right-handed. They'd go into this plane polarizer, and you'd see both vertical and horizontal coming out. Same thing the other way around. If you block these, the left-handed would come out left-handed, and again, you'd have both vertical and horizontal. So either way, you'd see photons at this horizontal exit. But with both of them open, you don't see any photons there. And the interpretation put on this by quantum mechanics is usually that as long as you don't actually observe through which passage the photon went through, it's not an either path. And the way it acts thereafter is just as if you had never measured the circular polarization to begin with. It only ends up being circularly polarized here if you observed whether it was right or left in between. So it's claimed that the act of looking, by blocking one and seeing therefore that it was right when it went through, or blocking the other and seeing that it was left, the act of looking makes it circularly polarized. Otherwise, if both go through, it's going to be vertical coming out, because vertical is what went in, you want to do what went in, so you get vertical coming out and only see the vertical photons. So looking makes it so. Determining what it was here affects what the polarization is at the end. Now, the elementary wave theory does away with this mystery altogether. If both of these, let's suppose this one's covered, so only the right can go through. And first look at waves now, elementary waves coming from this detector. They'll go in the vertical entrance here, so vertical ones will come out. They go into the circular polarizer, and it would normally do both right and left, but you're going to block the left now. So the right-hand circular ones come through. And therefore coming out will be those right ones. And part of the right will be this vertical, and so the waves will arrive at the source. Pardon me. And as a result, photons will follow through, and you'll see them on the vertical side. Similarly, horizontal ones. Coming in here, they'll be horizontal. Coming out of this, again, you block the left, so you get right hand, circularly polarized. So that's what would come out and would stimulate the vertical, because the circular part of it is vertical. So again, waves would arrive here, stimulate the emission of photons, and they would then follow that through, and you would see particles at the horizontal exit. Similarly the other way, if you blocked the right and left the left open. If they're both open, then if vertical comes to here, this combination means that verticals will come out and you'll see waves here, so you'll see photons on that side. Pardon me again. The horizontal waves, on the other hand, would be horizontal here, going in. The two together cancel each other, so horizontal would come out, none of which would make it through here, and so no waves would make it to the source, and therefore no particles would end up being seen at the horizontal exit. That's exactly what quantum mechanics predicts. But at no point is there any issue of the observation of the photon determining its state. The photon itself is always in one state in either arrangement. If both of these are open, well, you have two waves, and they're coherent and recombine as I just described. If one or the other is closed, then the waves do the alternative thing, just as described. The particle then is either stimulated or not, and it is then seen at the end appropriately. It's not the case that somehow the state of the particle is changed or determined by whether you do or don't look at it. It's solely an issue of the waves and whether they do or don't interfere. Basically, the waves coming this way, if they take both paths, they interfere together and end up reproducing exactly what went in. So one of these undoes what the other one does to the waves. So this captures the whole behavior that's observed, but without any need to conclude that the act of looking determines the state, or that if you don't look, the act of not looking makes it different. Nothing changes. And you fully can explain why it is that you get nothing here when both are open, but you do get stuff here when one or the other is open. And it's fully explained in a straightforward manner without any need to conclude that anything is only what it is because you looked at it. It's not as if the photon somehow is in both of these states but neither one when these are both open, and only becomes one or the other when you look. It's rather that when both passageways are open, you get two waves coming through and ending up simulating particles or not accordingly. The waves take both paths. There's never issue of a particle taking both and not having either state unless you determine which. That whole issue never arises at all in the elementary wave theory.
As I mentioned earlier, after Dr. Little made the video that you just saw, it dawned on him that a small variation in the experimental design would make a most interesting experiment in which quantum mechanics or wave-particle duality would predict different results, different outcome than the theory of elementary waves. In particular, he thought to introduce a new screen which would be transparent but able to be turned into opaque in a nanosecond or two, and this screen would be introduced between the C and the C- polarizers thus. At the beginning, the screen would be transparent so that elementary waves can pass through it, but as soon as they pass through, we turn the screen opaque so that photons responding to those elementary waves cannot get through the screen. Using this apparatus, what we predict with the theory of elementary waves is that photons will arrive at the detector in the upper right, but no photons will arrive at the detector in the lower right. On the other hand, quantum physics would say that photons will arrive at both detectors. Thus, there's going to be a difference in outcome as to whether photons are detected or not detected at the lower detector on the right, where horizontally polarized waves or photons are supposed to be arriving. Now here is why we make these predictions. Let's start with the theory of elementary waves. At first, as you remember, the screen is transparent. A wave starting at the upper right detector traverses through the entire apparatus easily and arrives at the left-hand side where the photon source is located without any trouble. We've discussed this before. The C and C- apparatus of the two circular polarizers works to cancel each other out because the screen is transparent. Things, however, will be different with the detector in the lower right, which is for horizontally polarized waves. An elementary wave starting there will go into the apparatus, traverse it, and end up coming out of the C circular polarizer on the left as a horizontally polarized wave. It will try to enter through the vertical polarized port of the last polarizer on the left and will not make it because a horizontally polarized wave can't get through a vertically polarized port. Therefore, no elementary waves will arrive at the photon source on the left, and consequently, no photons will get back to that detector. That's why the theory of elementary waves says that that detector will be silent. Now let's turn to quantum physics. In quantum physics, nothing that happens prior to the emission of the photon should really make any difference. Thus, the fact that this screen between the C and C- polarizers was previously transparent shouldn't matter. It's now opaque. Thus, it's blocking the lower pathway between the C and C- circular polarizers. Thus, a wave, or a photon rather, coming from the photon source on the left comes through, goes across from C to C- as a right circularly polarized photon, continues as a right circularly polarized photon, and then is divided into a vertical and horizontal component and is detected at both detectors on the right-hand side of the experiment. So that's why quantum physics and elementary wave theory make different predictions for this experiment. Dr. Little has one reservation about this experiment. He wonders whether this screen, which is transparent, might itself be emitting elementary waves. We don't understand this completely, and so whoever builds this experiment and conducts it will have to figure out and worry about that problem. So in summary, there are at least 5 experiments in which the theory of elementary waves and the theory of wave-particle duality, which is the cornerstone of quantum mechanics, go head to head in the sense that they predict different experimental results, and only one of them can be found correct by the experiment. Now you might say, wait a minute, 5 experiments. There's a mountain of experimental evidence supporting wave-particle duality, but we claim that the other experiments can be equally well explained by either the theory of elementary waves or the theory of wave-particle duality, and thus do not provide a basis for differentiating or distinguishing which of those 2 theories is correct. If we limit our attention now to the 5 experiments just mentioned, 2 of those experiments have been conducted, and in both of those, the experimental results are consistent with the predictions of the theory of elementary waves and contradict the predictions of the theory of wave-particle duality or quantum mechanics. The other 3 experiments have been designed by us, 2 by Lewis Little, 1 by me, but not yet conducted. The 2 that have already been conducted are an excited atom placed in a resonant cavity, described by Dr. Little on another video, and the neutron interferometer, also described by Dr. Little elsewhere on this website. Of the 3 experiments that have been designed by us but are not yet conducted, one is the one that I just described in this video. And another one, designed by Dr. Little, is the one where there is a transparent screen in a modification of the double slit experiment. The 5th experiment that I mentioned, the one designed by us, the 5th of 5 experiments in which theory of elementary waves and the theory of wave-particle duality go head-to-head, is one designed by myself, a different variation on the double slit experiment, and found also on this website. So thank you very much for your attention.